Hello and welcome back. In the last part, we were talking about x approaching a number from the left or the right. And these are what are called one-sided limits because the inputs, or the x values, are approaching this number c, so c from the left or c from the right, from one side, either the left side or the right side. So note that if a one-sided limit is either infinity or negative infinity, then that's going to correspond with a vertical asymptote. This is something that we hinted at a moment ago, or in the last part. So here are the four ways that that could happen. You could either have the limit as x approaches, now I'm using a constant a to represent the x value that we're approaching. So let's say we approach a from the left and f of x is going to infinity. Well, that's going to mean that the graph is going up as you get closer to a. And so you're going to have a vertical asymptote at x equals a. Or you could approach a from the left and have the function values fall to negative infinity. In that case, you would also have a vertical asymptote. Again, remember that asymptotes are just lines that the graph gets closer and closer to. And in this particular case, the graph is definitely getting closer and closer to this vertical line. And actually, asymptotes could extend not just to lines, but other kinds of curves. But for the most part, we think of them in this course as lines. So then we have the limit as x approaches a from the right. So we could be approaching from the right. And we could have the function going up to positive infinity. So the y values going up to positive infinity. That's what the picture would look like. And then the limit as x approaches a from the right could be negative infinity, in which case the graph would fall down to negative infinity as we get closer to a from the right side. So these are the four different ways that you could have a vertical asymptote. Either left side, positive infinity or negative infinity, or right side, positive infinity or negative infinity. Those are the four different ways. Well, let's look at some familiar functions that have vertical asymptotes. So in example 4, we're asked to find the following limits. And here we've got the limit as x approaches pi over 2 from the left of tan x. And here I think it really helps to have a visual understanding of what tangent looks like. So the first thing we want to do is draw a picture of tangent. And we can just do a quick little sketch. So here's a little coordinate system, and we know that tangent goes from negative pi over 2 to pi over 2, has vertical asymptotes at the start and the end, and kind of goes up as you go to the right through the origin. This is the basic graph of one of the periods of tangent. It repeats after pi over 2 and before negative pi over 2 in an infinite chain of these same looking graphs, but this is just one period of tangent. And that's all we need actually, because we're going to be approaching pi over 2 from the left side. If we want to draw a little arrow to show our inputs are approaching pi over 2 from the left. And if you look at what's happening to the outputs, what are the outputs doing? If you said they're going to infinity, that would be correct. So we're going to write the limit as x approaches pi over 2 from the left of tangent x is equal to infinity, or positive infinity. Great. Well, what about the limit as x approaches 0 from the right of ln x? And here we're going to draw a picture of ln x. Remember that ln x has a vertical asymptote, x equals 0, and it goes through 1, 0, and kind of looks like that. So as you're close to x equals 0, the graph is down towards negative infinity, and then as you go to the right, the graph goes up, it's increasing up through 1, 0, and then keeps increasing, although at a slower and slower rate. After all, this is the inverse of the exponential, and so it grows at an exponentially slow rate. Not exponentially fast, but exponentially slow. So natural log grows really, really slowly. Now, we're wondering what happens when x approaches 0 from the right. So here's x equals 0. if our x values are approaching 0 from the right, that little arrow indicates where our red dot is being dragged to. And then we can think about the path that we're traveling along the graph, and that's going to be going down to negative infinity. As the x values move closer to 0 from the right, the y values are going to be falling down towards negative infinity. So the limit as x approaches 0 from the right of ln x is negative infinity. And what the heck, we'll box these. These seem like worthy things to box. All right. Let's take a look at the limit as x approaches 0 of 1 over x. So 1 over x. Remember what that one looks like? 1 over x is a hyperbola, but it's rotated, so it looks something like that. So it's like hyperbola that's opening in the quadrant 1 and quadrant 3. It also has asymptotes. It's got a vertical asymptote at x equals 0 and a horizontal asymptote y equals 0. This is 1 over x. And now we can use this graph to indicate what's going on, to help analyze what's going on to the y values of 1 over x as the x values approach 0 from the right. So here's approaching 0 from the right. And the y values, if we go up to our graph, are going to be shooting up to positive infinity as x approaches 0 from the right. Now we're looking at what happens when x approaches 0 from the left of 1 over x. So we can reuse this same graph of 1 over x, but now we're going to be approaching from the left. And here, looks like that graph is just falling down to negative infinity. The y values keep going towards negative infinity. So to summarize example 4, it really helps if you can have a visual picture of these functions. Now that's not going to work for every function. Some functions are just complicated and we need some other tools to be able to evaluate them. But this gives us a way of tying a limit of a function that we know about and whose graph we know about to what we've just been learning about how to visually understand limits. So in other words, if you can graph the function, that graph, that visual picture, can help you understand what this limit is. Let's move on to horizontal asymptotes. So we saw an example of a horizontal asymptote in one of the previous examples, number 3. And we saw that the limit as x approaches infinity of the function was some number, like it was 3 in our example. That's going to correspond with a horizontal asymptote. That's a line that the graph is going to get closer and closer to as x moves to the right, as x goes to positive infinity, or as x moves to the left towards negative infinity. So in either case, if the limit as x approaches infinity of f of x is equal to L, or as you go to negative infinity, you get L as well, then you're going to have a horizontal asymptote y equals L. So an example that's shown off to the right is the limit as x approaches infinity of inverse tangent of x. And remember, the graph of inverse tangent looks like the graph of tangent, but it's rotated about the y equals x line. It's flipped about the y equals x line. So those vertical asymptotes that were negative pi over 2 and pi over 2 that we just saw a moment ago, let me scroll up, these vertical asymptotes at negative pi over 2 and pi over 2 become horizontal asymptotes. Let me draw them here. Negative pi over 2 and pi over 2. And the whole graph just swivels about the y equals x line to get the inverse function. That's how you get the inverse functions, is you swivel your graph about the y equals x line. So there's inverse tangent. It's a great example of a function that has 2 different horizontal asymptotes. A lot of graphs, like of rational functions, they're only going to have 1 horizontal asymptote at most. But here's an example of a function that has 2 horizontal asymptotes, which makes it a great example to work with. One to remember. Now here, if x is approaching positive infinity of inverse tangent, well, looking at the graph, the y values get closer and closer to pi over 2. That horizontal asymptote, y equals pi over 2. If you see this limit is pi over 2, then inverse tangent will have a horizontal asymptote y equals pi over 2. In example 5, we're going to look at some other familiar functions. So here's 1 over x. We graphed 1 over x before, but I'm going to draw one more graph of it. Here's the 1 over x graph. It has those vertical and horizontal asymptotes. So here it says find the limit. Limit as x approaches infinity of 1 over x. Well, the visual for the inputs is movement to the right along the x-axis. And then to figure out what the outputs are doing, we're going to travel along the graph, thinking about what the y values are doing as we're traveling along the graph in that direction. And it looks like the y values are just getting closer and closer to 0. So we'll say that the limit as x approaches infinity of 1 over x is 0. Let's look at e to the x. Remember that e to the x starts off close to 0, goes through 0, 1, and then blows up to infinity. There's this horizontal asymptote, y equals 0. There's a quick sketch of e to the x. Now here we're looking at the limit as x approaches negative infinity of e to the x. So our eyes are going to be moving to the left. So what's the limit as x approaches negative infinity of e to the x? If you said 0, that would be correct. As we're following along the e to the x graph, going to the left, the y values are getting closer and closer to 0. Box these again. I like boxing. That was a terrible pun. I can't believe I never thought of that pun before. All right. Now, these graphs, or these functions, 2 minus e to the x plus 1 and 2 minus e to the x plus 1, it's the same function. So we can recycle that graph once we have it. These ones are not quite our basic functions, but we can still graph them. If you remember from pre-calculus, you learned about function transformations. And all this is the e to the x graph. But what's the x plus 1 doing? That's a shift to the left by 1. What about this negative in front of the e to the x? Yeah, that reflects about the x-axis. What about this 2? What's that going to do? That shifts the whole graph up by 2. So we're shifting the graph of e to the x to the left by 1, then reflecting about the x-axis, and then shifting up by 2. Now, without going into the detail of all those steps, we're going to jump right into sketching it. And one thing is we can use some key points and figure out where they're going to help us out. So here we have this horizontal asymptote. If we shift to the left, it doesn't do anything. If we reflect about the x-axis, it doesn't do anything. But then if we shift up 2, that's going to do something. It's going to shift it up 2. So our new horizontal asymptote is up there. And the 0, 1 point, if we shift that to the left by 1, and then we reflect about the x-axis, and then we shift up 2, that's going to put us at a point right here. So here's negative 1, comma, draw this a little bit better. Here's 1, here's negative 1. So we're right there. Okay, and we could do another point, but the general idea is that this graph is going to be going something like this. And this part of it, by the way, doesn't have to go it can cross the y-axis. It doesn't have to, there's no vertical asymptote there. E to the x doesn't have vertical asymptotes. So here's the graph of 2 minus e to the x plus 1. Now that we've got the graph, we can evaluate these limits. The limit as x approaches negative infinity is what here? Well, if x is going to negative infinity, we're moving to the left. Our inputs are moving to the left. So as we're traveling along the function going to the left, looks like those y values are getting closer and closer to that horizontal asymptote that's at 2. So the y values are getting closer and closer to 2. Now, the other limit says find the limit as x approaches positive infinity of the same function. So here we're going to be thinking about our inputs going to the right. Now, we didn't really draw that much of a graph to go all the way over there, but so we'll just do as much as we can. So we're traveling along the graph with the inputs going to the right. Traveling along the graph where the inputs going to the right. So we're traveling along this part of the graph. Where does it look like the y values are going? If you said the y values are going to negative infinity, that would be correct. They just keep falling and falling down towards negative infinity. Those y values keep going down. They're going down. All right, so there's the limit as x approaches infinity of 2 minus e to the x plus 1. It's negative infinity. Now we're going to look at some other ways of thinking about this. One of them is going to be a numerical kind of way, which might be preferred in this particular case. But it's helpful to, initially at least, know that you can tie a limit of a function that you can graph to its graph. Once you have the graph, it's easier to get a real visual of what's going on and evaluate your limit. Well, that's all for this part. Thanks so much for watching, and see you in the next part.